We've seen previously how to find the arc length of a curve for a function y equals f of x. We've also seen how to do that for a parameterization where x equals f of t and y equals g of t. Now we're going to look at how we might find the arc length for a curve that's defined using polar coordinates r equals f of theta. Recall that when x is a function of t and y is a function of t in a parametric equation, we know that the length of the curve from a to b is given by the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Recall also for a polar curve r equals f of theta, we know that x is equal to r cosine theta and y is equal to r sine theta. This means that in this situation, we can treat theta like our parameter t. When we do that, we get a new formula for our arc length. Replacing t with theta gives us that the arc length of a curve between the values theta equals a and theta equals b is going to be the square root of dx d theta squared plus dy d theta squared d theta. Ideally, we'd find a way to simplify this formula so that we don't have to rewrite our polar equation in terms of x and y. We can use the familiar relationships between x, y, r, and theta in order to do this. In particular, if we write x as f of theta cosine theta and y as f of theta sine theta, then we know that dx d theta is f prime of theta cosine theta minus f of theta sine theta. That follows from the product rule. And similarly, dy d theta is f prime of theta sine theta times f of theta cosine theta. Squaring both terms then gives us that dx d theta squared is f prime of theta squared cosine theta squared minus 2 times f prime of theta cosine theta sine theta plus f of theta squared sine squared of theta. dy d theta looks similar but slightly different. It's f prime of theta squared sine squared of theta plus 2 f prime of theta cosine theta sine theta plus f of theta squared times cosine squared theta. It's a lot of algebra and a lot of multiplying, but the good news is when we add those two terms together, things work out nicely for us. The negative 2 and the positive 2 make the middle terms disappear. The sine squareds and the cosine squareds turns into 1. And we end up with the fact that dx d theta squared plus dy d theta squared is equal to f prime of theta squared plus f of theta squared. Putting all these ideas together, we see that our arc length, which was the integral from a to b of the square root of dx d theta squared plus dy d theta squared, becomes the integral from a to b of the square root of f prime of theta squared plus f of theta squared d theta. And we can calculate that arc length without ever having to change out of our polar coordinate system. Let's go ahead and use our formula to calculate the circumference or perimeter of the circle r equals a sine theta. So we know that that is going to be a circle that has a radius of a over 2. And geometry tells us that the circumference of such a circle is 2 pi r, which is going to be 2 pi times a over 2, which is a times pi. Let's see if our formula confirms this. So recall that in order to carve out one rotation of this circle, to get one perimeter of this, we're just going to go from 0 to pi, right? Our theta values are between 0 and pi. We also know that if r equals a sine theta, then f of theta is a sine theta, and f prime of theta is a cosine theta. Well, that means that f of theta squared is a squared sine squared theta, and f prime of theta squared is a squared cosine squared theta. So our formula tells us we're going to take the square root of f prime of theta squared plus f of theta squared d theta. Simplifying that, we get the integral from 0 to pi of the square root. I'm going to factor out an a squared We have a cosine squared plus sine squared left inside there. And of course, we know that that is equal to 1. So this becomes the integral from 0 to pi of the square root of a squared d theta, which is of course just the integral from 0 to pi of a d theta. Taking our antiderivative, we get a times theta, and we're evaluating that from 0 to pi. That gives us a times pi minus a times 0, which is of course just equal to a times pi. Let's tackle one more example. This time we're going to look at the length of the spiral r equals 2e to the 2 theta. And we're going to restrict theta to 0 to the natural log of 8. So we're going to, if r is equal to 2e to the 2 theta, that's the same as saying f of theta is 2e to the 2 theta, which means that f prime of theta is going to be 4e to the 2 theta when we apply the chain rule. F of theta squared is 4e to the 4 theta, and f prime of theta squared is going to be 16e to the 4 theta. So our arc length is going to be the integral from 0 to the natural log of 8, our bounds for theta, of the square root of f prime of theta squared plus f of theta squared d theta. We can obviously add the terms in the inside there, and we get 20e to the 4 theta. Not really sure why I made that so long. Oops, erase the whole thing. There we go. I'm going to split that up. So we're going to get the square root of 20. I can move that to the outside. We'll deal with simplifying that in a minute. And then we get the square root of e to the 4 theta, d theta. And that is going to become 2 times the square root of 5 times the integral from 0 to ln of 8. The square root of e to the 4 theta is e to the 2 theta, d theta. Now we get to take an antiderivative. So we have 2 square roots of 5 times the antiderivative of e to the 2 theta is going to be 1/2 e to the 2 theta, and we're evaluating that from 0 to the natural log of 8. Our 2's cancel, and so now we have the square root of 5 times e to the 2 natural log of 8 minus e to the 0. Well, that's the square root of 5 times e to the natural log of 8 is 8, so we get 8 squared minus 1, which is 63 square roots of 5. All right, wrapping up everything we've seen here. We know that if we treat theta as a parameter, like we did with t, then we can reuse the hard work we did in learning how to find the arc length of a curve defined parametrically. And we can use that to then find the arc length of a curve defined using polar coordinates, so that the length of that curve is going to be the integral from a to b, where a and b represent the values of theta for our upper and lower bounds, of the square root of f prime of theta squared plus f of theta squared, all d theta.